Good morning, ladies and gentlemen. I'm Hisao Matsunaga from Kyushu University, Japan. This is the original title of my presentation, but after the submission of the abstract, I realized that the time is very limited, so I changed. Today, I'd like to focus on only the fatigue crack growth properties. Thank you. Last night, I made an investigation about the ongoing project on the structural integrity of the hydrogen pipelines worldwide. I found so many research projects. We, of course, are doing, but I understand that so many experimental data are being reported from the world. But I understand we have some unsolved the problem on the hydrogen properties in hydrogen pipelines. For example, effect of microstructure and cleanliness. Sometimes they are investigating vintage materials. This is of course important, but effect of gas pressure that Chris made presentation today, and the effect of temperature, gas impurity. So many people are tackling various programs. And brittle mechanism. So everybody likes here. It. And this is also typical problem in Japan. Effect of seismic activity and the remaining line after the earthquake. This is very typical problem, especially in Japan. And also from the practical viewpoint, development of strength design and optimization, codes and standards. So we have so many problems. And in this presentation, I'd like to focus on the effect of temperature and gas impurities. So this is a background. Experimental data that I'm showing is obtained in the collaboration between the Impex Japanese company and the Kyushu University. Also in Japan, they are operating a pretty long natural gas pipeline in the middle of Japan. And they are planning to repurpose the existing natural gas pipeline for hydrogen. And I understand that they are, from the world, they are reporting a great amount of experimental data, but most of the experimental data are obtained at the room temperature, but not the low temperature, but high temperature. But if we look at the climate, so for example, in some area, in some cities, we experience so very cold temperature. Sometimes in Japan, so also in Japan, we sometimes experience minus 20 degrees C or minus 30, even lower. That's why, so to ensure the safer use of the pipeline, maybe we need to obtain the experimental data at various temperature. And it is well known that the high fatigue crack growth properties drastically increased in the hydrogen gas. And some people are trying to investigate the effect of temperature, but under the cathodic charge, not in hydrogen. So the objective of this study is, this is a question, how about the temperature dependence in hydrogen gas for the fatigue crack growth properties or X60 pipeline steel in 10 megapascal hydrogen gas? We prepared this X60 seamless pipe, as shown here, and we made a fatigue crack growth specimen. This is the shape and dimension. And we performed fatigue crack growth testing, 2 types of fatigue crack growth testing in accordance with ASTM standard. One is a delta P constant testing at 3 different temperatures to obtain the DAD and delta K data. And the second one is the delta K constant test to obtain the relationship between the acceleration ratio and frequency. Also at the various temperatures. This is a result, DAD and delta K curves obtained in the delta P constant test. as you can see here in air, the open mark shows the experimental data in air. So particular growth was independent of temperature. And in hydrogen gas, this is a solid marks indicates experimental data. The particular growth was accelerated at every temperature, the degree of which was independent of temperature. This is a practically very welcome result. And if we observe the fracture surface, for example, at delta K of 30, this is the fracture surface, room temperature -10, -20. This is the air and or nitrogen and hydrogen in the downside. So briefly, I can say that the fracture morphology was similar between room temperature and lower temperature. And then I show you the result of delta K constant testing. That means acceleration rate as a function of the test frequency. So this is a bit complicated, but interesting. At room temperature and -10 degrees C, the particular growth acceleration rate fell within the range of between 10 and 25 times, independent of the test frequency. But if we look at the result at -20 and -30 degrees C, the acceleration decreased at 0.01 Hertz, which was nearly equivalent to that in nitrogen gas. This is also good news in the practical viewpoint. And so okay, we made a fractographic observation, but I skip it. But the question is why? Why we have this kind of deceleration, the lower frequency? The first possibility that reminds us, it might be the inhibitory effect of oxygen impurity. Maybe everybody may think about it. So as you may know, Sandia team reported the effect of such an impurity effect. And they reported that the transition point is increased with an increase in the oxygen impurity. And under the oxygen impurity, the particular growth acceleration is mitigated with a decreased test frequency. And based on the physical modeling, they propose this kind of equation. But according to this equation, lower the temperature, the greater the inhibitory effect. So firstly, we saw that maybe the possibility during the testing, did oxygen impurity level in chamber increase with time? We always think about it. And so to confirm this kind of tendency, so we performed additional testing. That is a testing in hydrogen, but including oxygen impurity at 100 volume ppm. This is the result. At room temperature like this, at room temperature, particular acceleration was mitigated at every test frequency like this. But at -10 degrees C, the particular growth was accelerated only at 1 Hertz. And -20 and -30 degrees C, the particular growth was accelerated at 0.1 Hertz like this. And each fracture surface reflected the acceleration and non-acceleration. So this is a summary for the frequency dependence. So this is the result in hydrogen gas, including oxygen impurity. And this is the result in pure hydrogen. So it's very complicated. I cannot understand the interpretation at present, but the result is very complicated. But if we think that the oxygen impurity is the reason, so there is some discrepancy. So the result suggests that the mitigation effect of oxygen impurity is less effective at lower temperatures. How much? How many? 5 5 minutes?
Yeah.
Good. So anyway, I have no clear answer to show you today, but I'm pursuing the mechanism and influencing factors. So this is the summary of my talk. I'd like to emphasize no temperature dependence was observed in the maximum acceleration rate down to minus 30 degrees C. That's a good news. But the mechanism of the temperature dependence in low temperature hydrogen is currently unclear. Probably another dominant mechanism aside from impurity effect may exist, but further investigation is ongoing. Thank you very much for kind attention.